Okay, so just a short little video about enthalpy diagrams. And in an enthalpy diagram, what happens is we've got compounds that are starting at a certain amount of energy. They give that a specific name called enthalpy, and they use an H to indicate. So let's think back to our example when we did our bottle rockets. We mixed hydrogen with oxygen, and that started at a certain amount of energy. Okay, whatever that amount of energy is, it's in the form of bond energy. And what happens is we've got two molecules of hydrogen, two molecules of oxygen. And what happens is they'll begin to react. And in order for them to react, we have to put energy in order to get them to go. And so what was that energy? Do you remember that energy that we had to put in to get this reaction started? Well, it was in the form of a match or that flint stick that we had that we were able to light. And what happens is, as the reaction proceeds, we begin to form what's known as the activated complex. That's the in-between state between the reactants and what we'll see in just a minute, what are the products. Okay, and it's highly unstable, okay, because it's the highest energy. The highest energy typically molecules have, the more unstable they are. And so eventually what happens then is the reaction proceeds and we lose some energy in this particular reaction. Some reactions gain energy. There's a special name for each of those. So we produced, in the end, water molecules. In this particular one, we produced two water molecules. So let's go ahead and name a few things here. First of all, this is H sub R, the enthalpy or energy of the products. Again, this is what the amount of energy the products start with. We also have the enthalpy of the enthalpy of the reactants, the enthalpy of the products. Now notice in this particular one we lost energy. Okay, so it gave off energy, and you can see that it was obvious. I mean, we had an explosion of fire and sound, if you remember that particular reaction. And then we've got a couple other things. We've got the delta H. Anytime we do delta or change of something, it's always going to be, remember, final minus initial. So final minus initial. So really it's the HP subtract the HR. In this particular reaction, if you notice, we're going to have a negative sign on this one. This right here is the energy of activation. And so what happens is this is the energy that we have to put in order to get the reaction to proceed. Okay? This right here, energy of activation, is what's known as the rate determining step. Notice it's always where you start to the highest point. So that was the energy of the match that we had to light in order to get to start. Okay, now this is the rate determining step. Here's what that means. Ready? Let's say, for example, we had a lower activation energy. Okay. Now, what happens is that will produce a faster reaction, and here's why. It's not that the molecules themselves can get up and over the speed bump faster, okay? Not that one molecule can get up and over faster. It's that now more molecules, it's real important to have enough energy to get up and over the speed bump, okay? And if you remember this, we had an equation or a formula for reaction rate. So the reaction rate, remember, was change in quantity over a change in time. Okay, so what happens is if we get more molecules that are now able to get up and over the speed bump, our change in quantity increases. So therefore, our reaction rate increases as well. So that's why that's the rate determining step. So the lower the activation energy, the faster the reaction. What's going to happen is sometimes we have really, really low activation energies. And that would be something that's very unstable, maybe like nitroglycerin. Something that has a really high activation energy doesn't take much, it takes a lot of energy to get it started. Okay, think about maybe like a block of wood or something. That takes quite a bit of energy to get that wood to light. So here's just a few definitions that we talked about. That's the reaction energy, enthalpy of the products and reactants. Delta H is the change in enthalpy. Again, products minus reactants, or final minus initial. And then EA is the energy of activation. It determines the rate, again, because if it's smaller, more molecules have enough energy to get up and over that speed bump. And then that's the activated complex, that in-between step. It's really unstable because it's the highest energy. It's not quite the products, it's not quite the reactants. All right, last couple things, endothermic reactions and exothermic reactions. So first of all, let's get an idea. Let's use magnets for example. Let's say our magnets represent our atoms, and what happens is, in order to break magnets apart, let's say they're stuck together, especially if they're strong ones, we have to put energy in to break those magnets apart. Same thing with atoms. In order to get atoms to break apart, you gotta put energy in. But then when they form new bonds, that's when they give off energy. Okay, so very important to remember that. So magnets, we got to put energy in. The atoms, we got to put energy in to break them. New bonds form. When a chemical reaction happens, we have all sorts of bonds being broken and new bonds are being reformed. If the overall change in energy is of the new bonds being formed is greater, well, then we have energy being released. If the overall energy is greater required to break those bonds, then we have energy that has to be put in to get that reaction to go. Okay, so a couple things. Exothermic reaction. Okay, exothermic reaction, heat is exiting. Okay, so if we look at our graph here, that was the first graph we saw, was an exothermic reaction. Okay, if we remember this right here, that's our delta H. And if you remember this right here, where you start to the highest point, that is our E sub A, or energy of activation. So notice in this reaction is losing energy. Okay, it's giving off energy. Products are lower than the reactants that we start with. All right, something important, let me go ahead and add this over here. In an exothermic reaction, you're always going to find the energy on the right side of the equation. Okay, so that kilojoules represents our energy. So very important in an exothermic reaction. So, real quick, exothermic reaction, a good example would be like a hot pack. Okay, hot pack, when you break the inner parts of a hot pack, they give off energy. It's because energy is being lost. More energy is being given off when new bonds are formed than what's required to break those bonds. You're always going to have bonds that are being broken and reformed. It's what's the net gain when that happens. We have also what's called an endothermic reaction. And a good example of this would be a cold pack. Let's go ahead and draw a chart for an exothermic or an endothermic reaction. Heat is absorbed in an endothermic. What that means is if we start at a certain amount of energy, we're going to end higher than what we started with. So what happens is we have to put energy in order to get that reaction to proceed. So this would be a cold pack. And so what happens in a cold pack, energy is absorbed from the surroundings. And what happens is there's a lot of energy that's required to break bonds. Now you may say, wait a second, that doesn't make sense. Energy is going into the cold pack and it feels cold. Yeah, here's why. It steals energy from the surroundings and converts it from thermal energy into bond energy or chemical energy. If you remember at the beginning of the year, we went through the 13 types of energies. It's doing an energy conversion, converting from thermal energy to bond energy. That's why it doesn't feel hot. That's why it feels cold, because it steals energy from the surroundings. So if this is the case, in an exothermic reaction, delta H is negative. Delta H is positive, okay, for an exothermic reaction, for an endothermic reaction. Okay, and then let's go ahead and label 2 on this one for an endothermic reaction, or E sub A. It's always where you start to the highest point. That's our energy of reaction. So we got to put a ton of energy in to get that reaction to proceed. Okay, last one. As you would expect, endothermic reaction, energy is on the left side of the equation. Okay, that will conclude our endo and exothermic reactions.